GM, hello everyone. Welcome to today's session, and I am today's host, Joy. Thanks everyone for attending this class, and hopefully you had an awesome time last Saturday for our first class. And today we're very happy to invite Yi Sun, who is the co-founder of Axiom and also assistant professor at University of Chicago, who obtained a PhD from MIT. And today he is going to talk about adding ZK-based reflections to the EVM with Axiom, how it works, and what's next. I'll pass my mic to Yi Sun, and we can start our classes today. Welcome.
Hey everyone, thanks for having me here. So as Joy mentioned, I'll be telling you guys about Axiom, what it does and what it works, and what we're working on next. So first, I want to start by talking about the problem that we're solving, since it's not quite an obvious one. And feel free to interrupt with questions at any time. I'll be monitoring the chat as well. So the problem our starting point here is that smart contracts on Ethereum and actually any blockchain can't really access that much data today. And the reason for that is, frankly, that although there's a lot of on-chain data, smart contracts can't access history at all. So if you look at this Pudgy Penguin listing on OpenSea, and you try to identify which of the data points on the page a smart contract can actually access, it's really only the owner. So in this case, the owner is Zac Efron, but all of the transaction history, the previous prices, or the previous owners is simply not available to smart contracts. And this isn't a design flaw in Ethereum. Instead, it's actually something necessary to maintain the decentralization of Ethereum. If we forced every validating node to access the full history, that would be equivalent to forcing every validating node to be an archive node. And what's the consequence of this? Well, developers obviously try to work around it. And there are basically two ways to get around this issue. The first is to pay more. And what that means is that you store more data in your contract state, which creates some negative externalities on all users of your contract. As an example, Uniswap pays a little bit of gas on every trade to compute time-weighted average prices on both V2 and V3 pools. So this works and is pretty trustless, but has this additional cost. The second possibility is to basically reduce your security. That means instead of computing something on-chain, you just use a trusted oracle, which most frequently is simply a number computed by a protocol team and put trustlessly on-chain. And so these are kind of the two choices we see in the market today. And developers face, frankly, painful choice between these two options. And so the starting point for Axiom is the question of how we can scale both data access and compute for smart contracts in a way which is application specific and cuts through this trade-off. And the property of blockchains that we use is that actually in every blockchain, the current block will commit to the entire history of the chain. And so what that means is that if we access this commitment, then we can try to decommit to previous history using cryptography. And so I want to note that this doesn't involve coming to consensus on anything. It's just every node can look at the current block and have a cryptographic guarantee of the history of the blockchain. And this holds not in Ethereum, not just in Ethereum, but in essentially any blockchain. Okay, so how would we concretely do this? So assuming that compute were no object, what one could do is to prove some Ethereum transaction from 1 million blocks ago, you could exhibit the block headers between the current block and 1 million blocks in the past, and check that the hash of each block header lies in the next block header. So that would establish that this past block is actually in the valid history of the Ethereum chain. Second, one could check that the relevant transaction actually lies in the Merkle-Patricia trie, which commits to all transactions in that block. So this is a valid cryptographic proof. And the only problem is that it's extremely expensive to do in the EVM. You have to do 1 million Keccak hashes, and actually the Merkle proof is also pretty expensive. So the problem with this is just that doing this natively in the EVM is way too expensive. So the starting point for Axiom is that we can address this issue by using ZK. Namely, we can do this extremely expensive check of the Keccak chain of block headers, as well as the Merkle proof inside ZK, and obtain a succinct proof that can be cheap to verify on chain. Moreover, this can let us actually scale these proofs. So instead of just doing a proof of a single transaction or a single historic state, we can group these together. And finally, we can compose these proofs with perhaps other operations we check in ZK. And so we've packaged this up into something we're calling a ZK coprocessor for Ethereum. What that means is we allow smart contracts to query Axiom on-chain and perform two operations. One is we index the queries and read historic on-chain data from the history of Ethereum. Secondly, we perform verified compute on that data. And when we finally come to a result, we generate a zero-knowledge proof that the result's actually correct. So once we verify that proof on-chain, the result is deposited in a trustless way for any other smart contract to use. And so what that means is that because we verify all results from Axiom using ZK, they actually have security that's cryptographically equivalent to that of Ethereum itself. So let me talk through the advantages that both of these steps give us. The first is that because we're actually reading from existing on-chain data on Ethereum mainnet, we're able to interoperate with existing applications without requiring any code changes. So unlike something like a rollup, where you have to migrate your on-chain application to the rollup to get the scaling advantages, we let you access the state of your existing application. Now, in the second piece, the verified computation part, we're able to do in ZK computations which might not be practical in an EVM, even a virtual machine on a rollup. Think of things that are much too large to go into an on-chain computation, like neural network inference or other large analytics computations. Okay, so that's basically what Axiom does. Let me now talk a little bit about how this all works. So I mentioned earlier that there are two pieces to accessing historic data. The first piece is that we have to do a Keccak chain of block headers to establish that a previous block was actually in the history of the chain. We actually do a trick to maintain a cache of all block hashes back to Ethereum Genesis. So as you guys may know, there's about 17 million such blocks. And so we certainly couldn't write just 17 million storage slots in Ethereum. That'd be way too big. So instead, what we do is we maintain a data structure called a Merkle mountain range of all block hashes. So a Merkle mountain range is a succinct way to commit to a list of block hashes that doesn't change too much on each update. So it's a small amount of data that maintains a single commitment to the entire history of block hashes of Ethereum back to Genesis. And so we have a contract on Ethereum mainnet that is continually updated to update this Merkle mountain range. And when we deployed that contract, we actually had to initialize it with the block hashes all the way back to Genesis by proving this Keccak chain of block headers in ZK. And I'll talk a little bit more about how we do that later on. All right, actually, right now. So how do we actually keep this cache maintained? Well, what we have to do is prove that the headers of each block form a chain. So we check that the header of this block in the middle here, the hash of that is present as the parent hash in the header of the next block. And the header of this block is present as the parent hash field in the header of this next block, and so on. So we can generate a zero-knowledge proof that the header of this block is in this block, all the way down for a chain of blocks. And what we want to do is to generate a zero-knowledge proof of that fact for a chain of 1,024 consecutive blocks. That's actually a pretty heavy computation, so we use aggregation to accomplish this. What that means is that on the leaf nodes, we generate zero-knowledge proofs of valid header chains for chains of 128 headers. Then we take a group of 8 such proofs and we organize them into a binary tree. So as I'm showing here, we take the first 2 and recursively aggregate them in a zero-knowledge proof, the second 2 and do the same thing, and the third pair and the fourth pair as well. Then we use recursive aggregation on top of each of these pairs to get to a zero-knowledge proof, which establishes the valid Keccak chain of 1,024 block headers. One thing to note is that because of this binary aggregation structure, we're able to do this all in parallel. That means we can operate on the first pair, the second pair, the third pair, and the fourth pair independently and on different machines. Okay, so what we do to get the block hash cache is to verify all of these proofs on Ethereum and then update our smart contract accordingly. Now that we have this cache, a Merkle mountain range of all block hashes on Ethereum, to prove the Ethereum state transactions or receipts into this Merkle mountain range, we check Merkle-Patricia trie proofs in ZK. So the Merkle-Patricia trie is a degree 16 trie, and to check the Merkle proof involves a combination of serialization and hashing, which I'll talk about in a little bit more detail later. And the reason that we wanted to have this Merkle mountain range commitment is it allows us to make claims about different blocks in the same proof. So for example, we could prove an account balance from one block, a contract storage variable from a different block, and then a block header from a third block, all in one zero-knowledge proof that's verified into the same Merkle mountain range, since it actually commits to all block hashes and therefore all blocks in the history of Ethereum. Okay, so just to talk a bit more deeply about what we're actually proving here, in every block of Ethereum, we have a number of fields in the block header. So there are a few more fields, but for us, the relevant ones are the block hash, the state root, the transactions root, and the receipts root. So we currently support all the fields in green on mainnet. And the important one here is the state root, which commits to the full account trie of Ethereum. That means for every account, we have the address, the nonce, balance, and code hash, and finally, the local contract storage, which is committed to in the storage root. So for those who don't know, the storage root commits to a mapping between slots and values. And when you write a smart contract in Solidity, all of your contract variables are encoded into this trunk. So on mainnet, we're able to prove anything highlighted in green here, any block header, account, or storage slot. And last week, we just shipped to testnet the ability to prove into the transactions root and receipts root. So that lets us prove any piece of data on the execution layer of Ethereum today. All right, so before diving into what we can do for developers, I wanted to pause to see if there are any questions.
If you guys have any questions, you can just type it in a group chat so that we can have a look at it.
Awesome. So I'll move on to just show you guys a little bit what the developer experience of using Axiom is today. And then I'll loop back to talk about what are the zero-knowledge proof ingredients that go into building this product. So we built an SDK to allow developers to use Axiom easily. So you can install it just through npm. And what we're going to do is use an SDK to build a query into Axiom and allow developers to use the results once it's been fulfilled. And so just to reiterate what we can prove, we prove blocks, accounts, and storage slots. And then we're also able to prove different pieces of the transaction and receipt data. And for transactions and receipts, you have to use our experimental SDK since this is unaudited code. Okay, so I'm going to walk through an example which will illustrate one type of query that you can make into Axiom. So suppose you want to make a smart contract that checks whether a user was an active user during the previous Ethereum bear market. So we're going to say that the previous bear market was between August 2018 and July 2020. And we're going to say that a user was active if they made a sufficient number of transactions during that time period. And so luckily we can track how many transactions an account made by checking its nonce at the first block and the second block and just taking the difference. I see a question in the chat. Can you expand a bit on proof generation and verification? Actually, I have a section after this developer portion that dives into that in more detail. Okay, so let's see how we can actually use Axiom to query the nonce at the beginning and the end of these two periods. So the first step is we have to make a configuration. So we'll specify the version. We're going to do this on testnet. And we have a mock feature, which lets you test more easily with mock proofs, which are proofs that are the same as the real thing, except for the actual proof part. Okay, so there's basically 5 steps. First, we have to build a query into Axiom. So how does that work? We create something called a query builder, and we specify what we actually want to query. We want to check the account data for this address, which happens to be Vitalik's address, at the first block 6 million or so. And then we also want to check the address data or account data for that address at the second block, which is around 10 million. So we add both of these queries to the query builder, and we call the build function and get a bunch of metadata relating to our query. And we specify each portion of the query is specified by a block number, address, and slot. So the next step is to call the send query function on chain on the Axiom v1 query contract. So we have an encoding of our query that we just created, and we specify an address for a refund if we don't fulfill the query, and then we actually send the query here. And just to note, if your query has already been submitted and fulfilled, then you can reuse the answer without getting the query fulfilled again. Okay, so our backend prover is constantly indexing this contract. And when we see queries, we start generating the proofs. And once we finish the proof generation, we're going to verify the proof on chain and deposit the result into the contract. And we always emit an event to notify you once that happens. Okay, so now the proof, your query has been fulfilled, the proof was verified on chain, and the result is on chain in this smart contract. The final step is for you as a developer to actually read the answer. And so to do this, we need you to actually, we actually Merkleize the answer on chain to allow us to put a large amount of data on chain in a way that does not incur too much gas cost. So we put the results into a tree and actually deposit the Merkle root of that tree on chain. So what we're doing here in our SDK is actually creating the tree with this get response tree function. And then we are getting the witnesses, this get validation witness function, for proving Merkle proofs into the Merkle roots of this tree. And so in this case, we care about the account response because we care about proving properties of different accounts. So other options we'd have here are data about blocks, accounts, or storage. Okay, so the final step is to actually use this verified data in your smart contract. So we're going to create this response structure, and we're going to write an NFT mint function. And what that function is going to do is first take in this response struct, which contains the information that you proved using Axiom, validate that data against the Axiom smart contract, and then if validation passes, then you can mint an NFT for the user. And so how does this validation go? So this is the part where you actually check that something was verified in Axiom to be part of the history of Ethereum. So what you do is simply call this rResponseIsValid function. The first three arguments here are some encoding of the overall query. And then the last three are facts about block headers, facts about accounts, and facts about storage slots. So in our case, we care only about the facts about the accounts. And so we're going to constrain that there are exactly 2 accounts. And further, we're going to use the values in that account. So if we look at the this first block, we're going to fetch the values of the first query. So we're going to have the block number, the nonce from the account, and the address from the account. And then in the second block, we're going to fetch the values from the second query. So that would be the end block, the end nonce, and the end address. So all of these values were already checked to be correctly read from the history of Ethereum by Axiom. And so you can operate on them in your smart contract, just like something you access on-chain. So if you go down, you'll see you can check, we want to check that the starting block was actually the starting block of the bear market, the ending block was the ending block of the bear market. And if that's not the case, we throw an error. We want to check that the nonces differed by the threshold we define to be an active user in the bear market. And we want to check that the address actually always corresponded to the address of the user seeking to mint this NFT. So all this, the last 3 blocks here are simply standard validation logic to mint an NFT. Okay, so that's sort of the flow for building an app in Axiom. If you want, you first create an query from the SDK, submit it on chain. We fulfill the query with a zero knowledge proof, and then you can use the resulting data in your smart contract. So to wrap up this developer section, just wanted to talk through a few classes of applications that we foresee Axiom being useful for. The first are applications in identity and governance. So we think that right now, airdrops are really done in a quite centralized way. Usually the team will monitor addresses and specify, how many tokens everyone should get. We think that the future of airdrops and incentivization on chain is for users to prove some aspect of their historic on-chain activity and then collect incentives or airdrops on that basis in a totally trustless way from an on-chain smart contract. What this allows, we think, is just much more fine-grained incentivization. So you might imagine that if you trade on Binance or NASDAQ and you're a high-volume trader, then you get a lower fee tier. So essentially, you're getting a volume rebate. And we think that the same thing should happen if you're trading on an AMM like Uniswap. Another interesting idea, which was surfaced on Twitter after we launched, is the idea of gating access to different protocols based on your history. So if you see this tweet on the top right, someone proposed building an old account hook for Uniswap. So that would allow only accounts who have proven that they are over, let's say, 1 year old to trade on a Uniswap pool. For a separate class of ideas, we think Axiom can be used to create essentially trustless oracles. So we have a demo on our site for trustlessly reading historic Uniswap TWAP oracles, but a couple other examples would include pricing Uniswap LP shares using historic data, checking historic health factors for maker CDPs, or settling derivatives to a trustless average of the gas price over the last day or week. And finally, for those who are interested in NFTs, we think we can actually create a pretty good oracle for the transacted floor price of popular NFT collections by just reading the feed of transactions from OpenSea. Now, there's a couple of wackier ideas I kind of have. There's a general theme that one purpose of on-chain protocols is to provide accountability for their participants. What that means is that your participants are doing something, and the whole point of the protocol is to either punish them or reward them for good or bad behavior. And so if the activity is actually on-chain, then Axiom can provide a very objective measure of whether some activity was good or bad. So a couple examples of this are proving from reading transaction history that a builder executed a sandwich attack, proving for an on-chain asset management protocol what an asset manager's Sharpe ratio or max drawdown or other aggregate statistics of their performance are, or settling on-chain insurance using historic data. So this is actually the first use case we had for Axiom. So the problem here is that if you're creating an on-chain insurance protocol, let's say you're building a market around whether assets are greater than liabilities in the lending protocol. What you want to happen is that if assets ever dip below liabilities, then some money changes hands. But in practice, this is very hard to check. So it's possible that the market crashes, assets dip below liabilities, and then they go back up. And then once they've gone back up, a user actually has no way before Axiom to prove that the guarantee was somehow violated in the past and collect their insurance payout. And finally, for another example involving MEV, we feel like we can use Axiom to prove where a transaction was ordered within a block. So in all these cases, Axiom is providing a very objective way of checking things which already happened on-chain. Finally, just to be a little bit more expansive, Axiom actually provides a way to do arbitrary on-chain asynchronous calls to off-chain compute. So we think this can be useful for adjusting DeFi parameters based on historic price trajectories. As an example, if you're running a lending protocol and your one user keeps really getting close to being liquidated, maybe you should adjust their LTV threshold. And another example, if you're running an on-chain batch auction, like in CowSwap, Axiom can be used to prove that your off-chain solvers are actually doing the right thing. Finally, to give a few silly ideas, we can actually prove various aspects of your on-chain reputation in a totally trustless way. You can prove that you're an NFT whale, you can prove that you used to own a lot of a token, and you can prove that actually your account burned quite a bit of Ethereum and gas. You can also prove that you traded quite a bit of volume on a Uniswap pool, or prove that you were a yam farmer back in DeFi summer in 2020. So we feel like there's quite a bit of surface area of what you can use Axiom for, and we're pretty excited to hear any ideas you guys might have for that. All right, so for the last part of this presentation, just wanted to talk through a little bit of background on the ZK technology that we're actually using to make Axiom possible. So I want to talk through what are the actual operations that we need to prove Ethereum history. So for us, there's three big parts. And we're building all of these using libraries in Halo 2. So the 3 steps are essentially RLP serialization, Merkle-Patricia tri-inclusion, and then recursion and aggregation. So let me talk through them in sequence. So first, what is RLP? RLP stands for recursive length prefix, and it's a way to serialize all of the data in Ethereum. It's frankly not a very amazing serialization method, but the rough contours are as follows. So you can serialize arbitrary nested byte arrays using RLP. So everything in RLP is either a byte array or an array of byte arrays. The serialization is recursive, and the key feature is that you can parse an RLP serialized byte array by first looking at a prefix byte, which tells you how long the next field is. And so what that means is that there are a lot of dynamic array operations in RLP parsing or serialization. So the key primitive we need in ZK is that we have is variable length array manipulation. So these are operations like indexing into array, selecting a variable length subarray from a bigger array, or concatenating variable length arrays. Just to give an idea for why this last one is useful, if you have a serialized data structure and you want to parse the different fields, then you would check that they concatenate with the correct padding to your original serialization. And the key tool we use here is a technique called random linear combination. Namely, if we have 2 arrays, AI and BI, then we can check if they're equal in O of n time by comparing this function we call their random linear combination. Namely, we take the entries of AI and view them as the coefficients of a polynomial, which is evaluated at a random value r. So in this case, if the RLC of 2 arrays is equal, then we know up to cryptographically high probability that the arrays are actually equal as arrays. Okay, so 2 questions in the chats. One is, how does Axiom generate the ZKP of off-chain computation other than data query? So today we actually have to write a custom ZK circuit for you, which is not a great UX. And we're working on a way to allow you to write the circuit yourself and deploy it within our system. Second question is, why does the transaction fail if the query has been submitted before? Actually, that's just a UX feature we put in. So if the query has already been submitted, then you don't need to request a new proof for the query. So you can actually directly read the result from our contract already. So there's no need to actually re-request the proof. Okay, so basically we handle this RLP serialization using this random linear combination technique. Okay, so what's next? So once we serialize all the data in Ethereum using RLP, most of the data on chain is actually committed to in what's called the MPT. So that's a Merkle-Patricia trie. And this is a degree 16 trie. And the relation to RLP is that every node in the trie is actually encoded using RLP. And so to provide inclusion proofs into this MPT, we have to use the Keccak hash, which is actually the most expensive part of our whole system. And then we have to use RLC to check that Keccak hashes of lower nodes are actually appearing in higher nodes. Okay, so we now have RLP serialization and Merkle-Patricia trie inclusion. And what we need to do is to take proofs of block headers and Merkle-Patricia trie proofs for accounts, storage, transactions, or receipts, and combine them together. So basically, we can prove some number of these in each proof, but when we want to make aggregate claims about many of them, we need to combine proofs. And so this procedure, as you guys might know, is called aggregation. And so what we do here is, given proofs like pi1 through pi n, we can create a recursive verifier, which checks that all of them hold up to some pairing that we're actually verifying on-chain later. And so to do this, we actually need quite a bit of ZK work. So we use Halo 2 with the KZG backend, and we recursively verify these KZG proofs. And so that means we need non-native elliptic curve arithmetic, and we need multi-scalar multiplication using this arithmetic. And we actually also wrote a pairing circuit for elliptic curves, but we don't actually end up doing the pairing verification in ZK. Okay, so those are like the ZK primitives that we need. So let me talk through how we actually achieve this. So we're using Halo 2 with the KZG backend, and we actually built our own embedded DSL within Halo 2 to have a faster development velocity. So that's structured as basically 3 libraries. So we have Halo 2 base, which is a collection of very basic gadgets, things like addition, division, range check, or indexing into arrays. And it has a very convenient interface that you guys can check out. On top of that, we built Halo 2 ECC, which is a library to do big integer and non-native elliptic curve arithmetic. And separately, we built this library Axiom E, which holds Ketchak, RLP, MPT, and account and storage proofs. And okay, we actually used quite a few external dependencies here. So for Axiom E, we needed to use the Ketchak hash from the ZK EVM. So we exactly lifted that and made it compatible with our system. And finally, for the aggregation, we used the Snark verifier library from PSE. So that actually originally used a separate elliptic curve and big integer arithmetic library, but we replaced it with our own for better performance and also a much more convenient multi-layered aggregation setup. So our final set of ZK libraries ends up being the 5 on this slide here. Okay, so last few minutes, I just wanted to talk through a little bit how our Halo 2 base library works, since I think we offer a bit of a unique perspective on a Plonk-based system that I haven't really seen elsewhere. So the point of Halo 2 base is we want it to be extremely flexible with the layout. So what that means is that for the same logical circuits, we want it to be able to generate a circuit that has either one column or many columns. And in the one column setting, the verifier is extremely cheap. So what we do is we always have only a single custom gate, which simply is A plus B times C equals D, where A, B, C, D are laid out vertically. So as you can see here, we're computing the dot product of 1, 3 with 2, 4 by turning on a gate in the first 4 cells. So we have 0 plus 1 times 2 equals 2. And then we turn on a gate in the last 4 cells. So we have 2 plus 3 times 4 equals 14. So here we've used our single custom gate 2 times. And as you can see, we're overlapping the 2 gates so that we have 7 total cells instead of 8 total cells. Although this seems like a pretty trivial optimization here, it actually ends up saving roughly 25% for longer dot products. And so everything we built in Halo 2 base just uses this single gate and a range check lookup argument. Okay, so why did we want to do this? Well, we use extremely homogeneous gates. And what that means is that when we have a circuit with a fixed number of cells, we can then choose how many columns to have. And then we can relay out our filled out cells across those columns. So if we want a very skinny and tall circuit, we could specify, for example, 1 column and put all the cells and all the gates in that column. Or we can have a very wide circuit that has shorter rows. And so using this setup, we wrote a base library which has inner product, range check, array indexing, bitwise operations, and comparisons. And something we actually found extremely surprising is that this is basically the most basic gate you could imagine. And we weren't able to get any performance improvement by adding more complicated custom gates or changing our gates into something slightly more complicated. Finally, one more optimization we made that actually made a huge difference, and we haven't really seen elsewhere, is to really minimize the use of lookup arguments. So as you guys might know, one common usage of lookups is just to do range checks in a cheap way. And so previously, we actually had enabled that type of lookup on every single advice column in our circuits. And we made an optimization where we actually specify columns where we're going to do lookups and only allow lookups on those columns. And then instead of having other logical activity happen there, we always copy lookup values to those special advice columns that have lookup enabled. So this reduces the amount of lookup arguments pretty dramatically, probably from having every advice column having lookup to usually just having one column of lookup. And we found empirically this improves our proving speed by about 50%. So this trick sounds pretty dumb, but actually we found it was the most impactful thing we came up with over many, many rounds of optimization. All right, so that's the quick summary of our ZK libraries. So wanted to pause again for any questions before just talking through our vision for what Axiom is going to become. All right, so just to give a sense of where we are today, you can query us on-chain to read any historic block header, account storage, and now in testnet, transaction or receipt from the history of Ethereum. And so this lets us actually mix and match things. So you can have an account from a block, a transaction from a different block, a storage variable from a third block. And then right now, to actually do computation on these, we have to write you a custom ZK circuit. So where do we think this is going? So if we think about what's the optimal way to read from the history of Ethereum and then do compute on it, I think it actually comes in 3 steps. So the first step would be to add all historic on-chain data. So we're only missing the beacon chain, and we're in the middle of adding that right now. Once we finish that, we think that the best way for developers to actually read that data is to do view function simulation using the ZK EVM. So that would entail basically having a type 1 ZK EVM that's compatible with all historic blocks on Ethereum. So if we're able to do the first 2 steps, what we would have is an archive node that's essentially running in ZK. And finally, although we think developers will want to read the history of Ethereum using view functions, we think that the actual compute on top of that should happen using a ZK native virtual machine. And so we're exploring different options in that direction today. So that's everything I had. So you can try us out live on mainnet. We just launched at the beginning of July. And we have a set of pretty comprehensive developer docs at docs.axiom.xyz to both help you use Axiom and also talk through all of the ZK circuits and all of the reproducible on-chain verifiers that actually power Axiom. And we have a Telegram group linked here for technical discussions about building on Axiom or the ZK stuff that underlies it. Yeah, so happy to stay on for a little bit for any questions. So I'll take them in order. So first is suggest learning resources for Halo 2. So if you go to our docs.axiom.xyz, At the very bottom, we have a set of intro resources for actually how to get onboarded onto ZK. So I would suggest that as a starting point. Next question, how much data does Axiom need to have to generate storage slot proof of A over C in a 1,000th block? I'm assuming you mean accounts in 1,000th block. Yeah, we actually just need to pull data from a standard JSON RPC node. So nothing very special. We draw from archive nodes, and then we generate zero-knowledge proofs of like client proofs that archive nodes give us. Rashab asked, what are the custom ZK circuits that are available right now? We have actually a pretty big library of ZK circuits. So most signature schemes, numerical functions, even some basic machine learning operations. The problem is actually that the integration has to be done custom. And so that's something we're working on to make more self-serve, since we recognize developers don't want to talk to us to have to deploy it.
Great, thank you, Professor. We actually collected some of the questions like backend from our students. We also have a bunch of students attending our offline sessions as well at our Singapore office. So the first question actually goes to, how can we use ZKP protocols to reduce query fees?
Yeah, so right now, basically, the core costs right now is actually on-chain verification. So we have to do a pairing on Ethereum, which is still relatively expensive. Once we have more query volume, what we can do is to start aggregating queries from different users. So that will amortize the cost of on-chain verification between different user queries. And so naturally, over time, you'll see our query costs go down.
Got it. The second question goes to, what is the difference between Axioms and ZK oracles?
Yeah, and as I mentioned, some of the applications we have essentially are the same thing as ZK oracles. I think the biggest difference is that we actually envision the post-processing compute playing a pretty big role going forward.
All right, another question is, if the consensus mechanism of the original blockchain changes or a hard fork occurs, how does Axiom ensure the consistency and integrity of the data?
Yeah, that's a great question. So if something is proved by Axiom on a branch of a blockchain that is on the wrong side of a hard fork, then it's as if that never happened. So one thing that's interesting about Axiom is we don't actually rely on consensus at all. We only rely on the fact that every block of a blockchain commits to its complete past. And so that means that anything we prove is always going to be objectively true on the chain that we proved it to. So we don't really have to worry about these consensus or hard fork issues.
Got it. Some student also asked, why was Halo 2 chosen in the underlying protocol? And what are the considerations behind this choice?
Yeah, so we chose Halo 2 for a couple of reasons. We found it to be the only proof system that met our criteria on all dimensions. So the number one reason is that Halo 2 was first developed by the Zcash team, and we feel it actually has the best security story among all proof systems. So Halo 2 has been running live for Zcash for, I think, over a year now. And it actually went through extremely rigorous audits from the Zcash team. The second consideration was the fact that it's fully open source, and it has a very robust open source community of contributors that are both examining the code, but also continually improving Halo 2. And the last consideration is that it can actually be verified on-chain. So there's this aggregation library that also provides EVM verification.
Got it. And another question is, can Axiom be combined with current ZK rollup solutions?
Yeah, Axiom can definitely work, I think, in a pretty complementary fashion with both ZK and optimistic rollups. So long as a rollup is actually EVM equivalent, then we can read from the rollup history. Another thing we could do is actually start verifying our proofs of L1 history and state on L2. There, basically, because every rollup already has a view of L1, that can be done in a fully trustless way.
Got it. We're aware that Axiom will continue to generate new on-chain proofs, which requires a consistent and stable provers to provide the computational power for ZK proofs. And it seems to have a very significant hardware expenses. So on that point, are there any cost reduction measures Axiom is considered right now? And for example, similar to Squirrel, consider taking advantage of community provided computing power?
Yeah, we're definitely interested in that in the future. I would say in the short term, we think the main cost reduction of proving is going to come from improvements in the cryptographic algorithms. So we think that ZK proofs can probably drop in cost by a factor of 10 to 100 without any sort of hardware changes. Yeah, that said, we are committed to opening up proving. And I think that's going to provide the best liveness guarantee.
Got it. I also saw another question in our group chat, which is about the hardware expense as well. Can you, Professor, can you also elaborate on that as well?
Yeah, so the question is about what are the hardware specs of the machines that we run on. Yeah, we tried to cost optimize a little bit by using several different types of machines. The baseline requirements are that the biggest issue is actually the RAM requirement. So we currently need between 200 and 300 gigs, depending on the specific query type. We do use GPU acceleration, and there we currently are using, I believe, NVIDIA A10Gs, but that's not actually a hard requirement. It's just that in the cloud, you kind of have to pay for these sort of GPUs. We previously did some experiments on consumer-grade GPUs, and the proving times were relatively similar.
Great. We still have 8 minutes. If you have any questions, you can type in the group chat, and also for the students here offline, if you have any questions, you can shout out to the professors so that we can have a last-minute review of what we covered today. All right. Do you guys have any questions? Okay,
Yeah,
go ahead.
Question I heard there is generating so can you explain more detail?
All right, so there is machine learning generate the proofs. Maybe Professor, you can elaborate a little bit more the details of how it can be generated, and also the applications of that.
Yeah, so I think the question is, can the compute here include machine learning type operations?
Yeah.
And the answer is that we basically treat, let's say, neural networks and other types of machine learning models as simply functions. So zero knowledge proofs can be generated for any type of deterministic function. And specifically, that can happen for neural networks. So I've written a couple papers last year on how to adapt sort of general purpose proof systems like Halo 2 to actually scale up ZK proofs for neural network models up to even the scale of ImageNet and larger data sets. I would say the main learning there is that the techniques that are currently being used to make neural network inference cheap on mobile phones and edge devices are actually really similar to the techniques that are needed to make inference cheap in ZK. And so it's just a matter of applying very similar optimization techniques to make the actual networks cheap to prove, and then applying carefully crafted circuits to do that. I'm actually pretty hopeful that we'll be able to scale up substantially more.
Great. Thank you. Last minute questions. All right. Okay, so one more question. So
when we send the query to the Axiom or with our data, we kind of expose our computation data to Axiom, right? So is there any mechanism from is there any mechanism preventing the data from leaking?
Yeah, the question is like, is there any sort of privacy guarantee?
Yeah.
So right now we're only operating on on-chain data, which is essentially already publicly available. So on the data, there's definitely no privacy guarantee.
Okay.
On the compute side, it might be possible to offer a privacy guarantee. Namely, one could prove that you're doing some computation, but not what. We don't currently offer that, but it's something we might consider in the future.
Okay. Thank you, sir.
All right. If we don't have any questions now, I think let's call it a day. And thanks, Professor, for this wonderful speech. If you guys still have any questions, feel free to drop the questions into the group chat, in our Telegram chat. We will help you to solve all these questions like later afterwards. All right, great.
Thanks so much.
Thank you very
for
much.
coming, everyone.
Thank you.
All right, thanks. Bye.